All right, everybody, welcome to the beginning of chapter 11, which is an incredibly broad chapter on water. This is a picture from the 1990 500-year flood on the Mississippi-Missouri River, which we'll be talking about much later in this chapter. To kind of illustrate how important water is, especially in rivers, I wanted to show you this kind of cool series of pie graphs. About as cool a series of pie graphs as one will ever see. So this pie graph here represents all the water in the hydrosphere, and what you see is the vast majority of it is in the oceans, and therefore without a whole lot of work, not really useful to people as drinking water. 2.8% of all the water in the hydrosphere is not in the oceans, and of that 2.8%, almost all of it is trapped in glaciers. So this is fresh water that, again, is not really accessible to most people. Later in this chapter, we'll spend a good deal of time talking about groundwater, which is our next largest reservoir for drinking water. We'll talk about what happens when groundwater gets polluted, what happens when rivers get polluted, and this vanishingly small slice of the hydrosphere represents all of these things that you see here. The one we're talking about at the beginning of this chapter is stream channels. So out of the entirety of the hydrosphere, 0.0001% of all water is actually in stream channels. So the first discussion I wanted you guys to have was about where your water comes from, because you should know. As you've seen in the news in the last several years, public water supplies are sometimes clean and sometimes not. And so that is a human rights issue, really, even in a country as well developed as the United States. So the first portion of this chapter really just has to do with characteristics of streams and rivers. And I'm going to show you two different animations of streams. What I want you to think about is what the average particle that is traveling down that stream, like what the motion of the average particle might be. So here is a river in British Columbia that is in flood stage. It is a bit pixelated. I probably could find another video for this. So you get the idea. There is a lot of water moving very fast. It's a crazy flood according to YouTube, so that must be true. So what I usually do here is I stop my class and I have my students actually sit there and sketch out the particle motion, and they look at me like I'm crazy, and that's kind of why I do it. But the particles in this river are moving incredibly randomly, right? I'll give you the word for that in just a few minutes. This next simulation is actually not a stream. Oh, well, that's how they move. Sorry. This is an animation. This is actually a simulation of really slow moving water, and this is an experiment where there are 3 dyes, red, green, and blue, and they're put in a thick fluid, and they simulate what happens when water moves incredibly slowly. They're going to put in the 3 dyes, and then they're going to spin it 5 times in one direction and 5 times in another. And I know it's slow and boring at the beginning, but it's very cool.
All right, now we're going to rotate these fairly slowly 5 times.
And I love that they hold it down like it is a serious thing.
Notice the flow is laminar because the Reynolds number is less than 1. Just 2? This will be 3. This is 3. 4. 5. Now we're going to go back. Backwards 1, backwards 2, backwards 3, backwards 4, backwards.
You can go half a rev.
Oh, I see.
Go one more.
It's good when you have a couple of coaches. Very good.
Come on, how cool is that? They went right back to where it started from. I love it. Okay, so in that stream, particles basically moved in one direction. So the stream where you had the really fast moving water, that exhibited what's called turbulent flow, while the second stream exhibited what's called laminar flow, kind of like the way water would move through a pipe in one direction. So then I stop and I ask students, what do you think are the big obvious differences between those two streams? And they come up with velocity. And I say, great, you're right. Velocity is what differentiates turbulent flow from laminar flow. So what do you think controls viscosity? Or not viscosity, wrong chapter. Velocity of water. And it takes a few minutes, but they pretty much come up with the two biggest controls of velocity in a stream. And one is the slope, how the gradient varies in different locations. And the second one is the volume of water, which is called the discharge, the volume of water that passes through at any one given time. So yeah, the steeper the slope, the faster the velocity, and the more water, the faster the velocity. So cool. Streams vary along their profile, and we call the beginning of streams the head waters of the stream, or the head of the river. And then it travels south in this case. Let's pretend it's traveling south. And as it does, you can see that the character of the river changes as we change from headwaters to mid-length, and then mid-length to mouth. So I'm going to illustrate that for you on Google Earth because I think it's kind of fun. And we're going to start with the Genesee River because that's close to us in Rochester. The Genesee River is the reason that Rochester is located where it is, and the Genesee River actually has its origins in the foothills of the Appalachian Mountains in Pennsylvania. So there's two tiny little creeks. There's one here that flows this way. You really can't even see the water. You just see really where the trees are that are soaking up the water. And then there's a tiny little creek here. And they flow together, and then they form this tiny creek that will one day become the Genesee River. So if you look here, the slope is fairly steep along the profile here, along the headwaters. There's very little discharge, and the river at this point is very, very small. And so as we move to the mid-length of the Genesee River, near like Avon, New York, which is about 45 minutes away if you were going to drive from the mouth, you see that the character changes significantly. So here's the river, and you can see that it's meandering. There's much higher discharge. The river is winding, and so meandering is what we call it when rivers kind of move back and forth. This is in a floodplain, so you can see that the floodplain of the Genesee River is roughly here. You can see there's some areas where a meander got cut off from the floodplain. That's right here, and that's called an Oxbow Lake. You can see this Oxbow Lake used to exist here, but it's dried up. So the character of the river has changed significantly. The slope, it's very flat here, is much less. The discharge is much more. The velocity is fairly slow at this location. The mouth of the Genesee River is kind of interesting. It is in the port of Rochester, right on Lake Ontario, and it is heavily engineered. So here is a pier that's about a mile long, and here is another sort of seawall, for lack of a better term, and here's where the Genesee River flows into Lake Ontario. And I really like, so in Google Earth, you can go to the time-lapse photos here, and we can go back a few years so you can really see this plume of sediment there we go, as you have it pouring into Lake Ontario. So the Genesee River itself is pretty brown, and that's because it's carrying a lot of glacial sediment along with it. And it flows into Lake Ontario here and creates a delta at the mouth. It's fairly heavily engineered. Those of you who live in Rochester, this is Ontario Beach State Park near Charlotte, and this is the pier. And even though it's a pretty beautiful beach, it's regularly closed, and part of the reason that it's closed is because there's a lot of bacteria in the water here. But the bacteria actually comes from closer, from near like Hamlin Beach, where there's basically nutrients that get put into the water from farming, and those nutrients flow in the same direction as the wind, which in this case is from the west. And there's all sorts of algae that will use those nutrients to reproduce, and they make these big algae blooms. And there's bacteria that live in the algae blooms. So the algae will float down, and then it gets stuck right here by the pier. And when those algae die, there are bacteria that live in the algae. So the higher the algae content here, the higher the bacteria content in the water. And that's why Charlotte Beach gets closed so very much. But it's kind of interesting. So if we look at this very real example, and then we go back to our idealized profile, we see something pretty similar, right? Where at the headwaters, there's not a lot of water, but it's fairly steeply sloping. And then we get into the mid-length where there's meandering back and forth. And then eventually we have a delta where at the mouth of the river where it flows into another body of water. The next thing we're going to talk about is a really important topic that really controls the behavior of streams, and that is its base level.